Hello everyone, today we're going to wrap up our polynomial notes by looking at even odd multiplicities, y-intercepts, and writing equations. So, even odd multiplicities. Essentially, this is what happens to the graph as we approach the x-axis. What happens to the zeros of the polynomial itself? To this end, we look at the exponents. If we have a situation where an exponent is odd, that graph will cross the x-axis at 0. If, on the other hand, our exponent is even, the graph is tangent at that 0. Now, tangent means we essentially touch it once. I've found in previous years that instead of tangent, people are often a little more comfortable with the term bounce. Let's say that if our exponents are even, we're going to bounce at that 0. Now this other part down here, there we go. This other part down here, if n is odd and greater than 1, the graph will have a wiggle where it crosses. The greater the odd number, the longer the wiggle. If you're going into calculus next year, put a star here, put an arrow here. This is important to know for future concavity problems. However, for the purposes of my class, if n is odd, the graph is going to cross at the 0. If n is even, the graph is going to be tangent or bounce at that 0. So what does that look like visually? If in our graph, in our equation here, we're told that f of x is equal to x plus 3 squared times x minus 1. What that means effectively is that we're going to have two zeros, one at x is equal to -3, another one at x equals 1. How do I find those so quickly? Well, we can remember that the x's lie to us. That's why we broke up with them. So x plus 3 is the same thing as x equals -3. X minus 1, that's the same thing as x equals 1. Because ultimately, these are the values such that x plus 3 is equal to 0, and x minus 1 is equal to 0. If x plus 3 is 0, x equals -3, and if x minus 1 is 0, x must be +1. If we take a look at our graph, at x equals -3, our graph approaches, touches, and then bounces back. That's because we've got a 2 as our exponent. 2 is an even number. That creates our bounce. Whereas at x equals 1, we have a crossing over from a negative field to a positive field. That occurs because our exponent here, even though it's not written, is the value of 1. So if we have an odd exponent, we're going to cross over. If we have an even exponent, we're going to bounce. Finding the y-intercept. So recall that the x value at the y-intercept is 0. Therefore, when it comes to finding the y-intercept, we're essentially going to follow all of our same rules that we've done for anything else, for linears, for quadratics. We're going to take 0 and substitute for all of our x's and simplify. Take all the x's, turn them into zeros, and simplify. Such that if you look at this basic equation, x minus 3 cubed times x plus 2 squared, substitute those zeros in, we get 0 minus 3 cubed times 0 plus 2 squared. That gives us f of 0 is equal to -3 cubed times 2 squared. Same thing as -27 times +4 f of 0 is equal to negative 108. Therefore, the y-intercept occurs at 0, negative 108. So for these next few, we're going to take all the information we've done so far in polynomials, our stuff from polynomial 1 and from today, and we're going to identify the zeros, y-intercept, and multiplicity of each of these problems. So for this first one, where we have f of x is equal to x plus 5 cubed times x minus 6 to the fourth power, first we're going to find our zeros, such that the x's lie to us. That's why we broke up with them. Our first x, this pointer wants to work. So, this first x value is equal to negative 5. And at that negative 5, we have an odd exponent. We've got a 3. So we're going to have essentially a crossover. Our second x value comes from our x minus 6. Well, if x minus 6 equals 0, then x is equal to positive 6. We have ourselves an even exponent there, so we're going to have a bounce. So that's our zeros, and that's our multiplicity of each. So let's take a look at the y-intercept. For our y-intercept, we're going to basically do f of 0. So 0 plus 5 cubed times 0 minus 6 fourth power. Well, that's essentially going to be 5 to the third power times negative 6. It's the whole negative 6 to the fourth power. Plug those into your calculator, and we'll get a y value such that f of 0 is equal to 162,000. So this will cross the y-axis just really high up. No, I won't have you graphing any of these things that have that high of a y-intercept. You might need to evaluate them. You might need to do what we did here, but you won't necessarily need to graph them out. Number 2. Here we have 3 different parentheses. So we're going to have 3 different x values. X value number 1 comes from that x minus 5. If x minus 5 is 0, then x equals positive 5. We have an even exponent, so that's going to be a bounce. Our next one, x equals negative 4. We've got an exponent of a 3, so that's going to be a cross. Last one, x plus 2 equals 0, therefore x is equal to negative 2. That has an exponent to the first power, even though it's not shown. Anything that's not shown, we could assume to be a 1. That's going to be a cross as well. Now we find our f of 0. Let's break this up from the previous problem. We have f of 0 is equal to negative, because we have a negative out front in our equation, 0 minus 5 squared times 0 plus 4 to the third power times 0 plus 2 to the first power. Simplify. F of 0 is equal to negative of negative 5 squared times 4 cubed times 2. So we essentially have negative 5 squared, that's 25. So negative 25 times 4 cubed, 64, times 2. Multiply all these together in our calculators. We're going to have a final answer of negative 3,200. So the y-intercept occurs at 0, negative 3,200. Last one, number 3. Here we have a small hiccup, but nothing too crazy. Because here we have the situation where we don't simply have nice, neat coefficients. Rather, we have our coefficients of, sorry, I don't know why the program's doing that stuff. We have our coefficients that exist as some value times x plus some other value. Here it doesn't change much. We're still going to have like our 2x plus 3 must equal 0. If 2x plus 3 is 0, well, first we're going to subtract 3 from both sides, then divide by 2. X is equal to negative 3 over 2. We have there an even exponent, so that's going to be a bounce. Then we have 3x minus 1. Well, if 3x minus 1 equals 0, then we add 1 to both sides, divide by 3. X is equal to 1/3. We have here a 3. That 3 means that we have an odd exponent, so this is going to cross over. Lastly, x minus 7. That's more used to what we're looking at, or looks more like we're used to seeing. X minus 7 equals 0. Therefore, x equals 7. The exponent here is 1, so it's going to cross over. Now do our f of 0 bit. Well, f of 0 is going to be equal to essentially 2 times that 0 plus that 3, the second power, times 3 times that 0 minus 1 to the third power, times that 0 minus 7 to the first power. Now, anytime we have 0 times anything, like we do here, 0 times anything is 0. So even though those coefficients made finding our zeros a little difficult, it actually makes the rest of the problem easier. Because this first part simplifies down to 3 squared. Then we have multiplied by negative 1 cubed multiplied by negative 7. 3 squared gives us 9. Negative 1 cubed gives us negative 1. And negative 7 is simply negative 7. 9 times negative 1 times negative 7 gives us 63. So f of 0 is equal to 63. All right, now for the last bit. Writing polynomial equations given the zeros. So if we want to write a polynomial function with zeros of negative 1/2, 3, and negative 4, we start off basically saying that these are the x values we care about. So x is equal to negative 1/2, x is equal to 3, and x is equal to negative 4. Now we need to put these in the format of x plus or minus some value. Well, x minus 1/2, that's going to become x plus 1/2. Remember, ultimately, these must equal 0. X equals 3, that's going to become x minus 3 equals 0. X equals -4, well, that's going to be x plus 4 equals 0. So I'm going to take these middle parts here, x plus 1/2, x minus 3, and x plus 4, and those are the components of our equation. So f of x is equal to x plus 1/2 times x minus 3 times x plus 4. Now the problem doesn't say to write it out in standard form. So I'm going to stop there if you are. Well, I'm going to stop there, so I'll stop there for this one because we don't have to go any further. The next one, though, we do have to take some things in consideration. But we're going to start off the exact same way. We want to write a polynomial function with zeros of 0, negative square root of 3, and positive square root of 3. So x is equal to 0. That's simply going to stay as x equals 0. X equals negative square root of 3. That's going to become x plus square root of 3 equals 0. X equals square root of 3. That's going to give us x minus square root of 3 equals 0. So we take our middle bits here. I'm sorry for the touchpad, folks. We have f of x is equal to x times x plus square root of 3 times x minus square root of 3. That's a plus sign there, I promise. Now, here's our little caveat. In these equations, we don't like having radical numbers. We don't like these square roots of 3. So we're going to multiply our x plus square root of 3 with our x minus square root of 3. If you recall, we have two binomials that are the same values except different operators. So this one being a plus, this one being a minus, that the middle terms when we FOIL are going to cancel out. So we only care about x times x, which is x squared, and the last part, positive square root of 3 times negative square root of 3, that's going to give us minus 3. Of course, we got the x out front. Now, you could leave it here, or you could take it one step further if you want to, because at this point, all we have left from standard form is to distribute that x value to give us x cubed minus 3x. So you can leave it as that, as x times x squared minus 3, or you can take it all the way to standard form with x cubed minus 3x. Either one of those would be appropriate. Either one would work. Now this last one deals with I values. Write a polynomial function with the zeros of -1, 5, 2i, and -2i. So just like before, we're going to start things off with our x equals -1, which will become x plus 1 equals 0. Then we have our x equals 5. That becomes That becomes x minus 5 equals 0. Then we have x equals 2i. That becomes x minus 2i equals 0. And then x equals negative 2i. That becomes x plus 2i equals 0. We then take these middle portions, x plus or minus a thing, and put them into our equation, such that f of x is equal to x plus 1 times x minus 5 times x minus 2i times x plus 2i. Now, since we have imaginary values there and there, we can't leave them as such. We're going to have to combine them. We're going to have to FOIL them out. But just like in the last problem, where we have x and 2i both different operators, all we really care about is the x times x, so x squared, and then negative 2i times positive 2i, which is negative 4i squared. We should recall from last units that I squared is the same thing as negative 1. This is actually x squared plus 4. And then we bring down the rest of our terms. We had that x minus 5, and we had that x plus 1. And that's our equation. If you have any questions, folks, please come by to tutoring, flex periods, or send me an email.